What? Open the door.
Okay, here we go. Extrema. Extrema refers to the functions maxima or minima. So there are two different types, really. We have local or relative extrema. It refers to the local relative minimum values or local relative maximum values. And then we have the absolute. So the absolute max is the highest point of the function. The absolute min is the lowest point of the function. A local max means that it is higher than all the other points around it, but it may not necessarily be the absolute max. So for example, I have a function here. At point D is the absolute maximum of the function on the graph because it is the highest point. Point A is the absolute minimum because it is the lowest point. Point C here is a local maximum because it is higher than all the other points around it, but it is not the highest point of the function. So that brings us to EVT. This is the unit of theorems. We've got EVT, we've got MVT, we've got IVT. So the extreme value theorem says this. If the function f is continuous and it is on a closed interval, then the function must have an absolute maximum value and it must have an absolute minimum value because of the extreme value theorem. But it's got to be continuous and it's got to be closed. So I have a function here. My function A is continuous and these are both closed endpoints. Therefore, the function is closed. Therefore, I know that it has an absolute max and I know that it has an absolute min. So these absolute extrema will occur at the endpoints or in the interior, but they have to exist if the extreme value theorem is true. So I've got absolute max is going to be at point C. So this is going to be at x is equal to C, which is in the interior. And my absolute minimum is going to be at x is equal to B, which is at the endpoint. And then I've also got a local minimum at x is equal to A. It's a minimum because it starts at the endpoint and then the function increases. Therefore, I have a local minimum at A, but it's not the absolute minimum. And that brings us to critical points, which you need to know. A critical point is a point in the interior of the domain of a function f, at which f prime is equal to 0, or f prime is undefined, and the point must exist in the original function. So I cannot have a critical point if the point doesn't exist. But the definition of a critical point, it's got to be in the interior, number one. The derivative must be 0 or the derivative must be undefined. And that is implying that the point actually exists in the original function. We use critical points to find extrema. Either maximums or minimums. In fact, extrema are always at critical points or endpoints. Let me say that again. Maxes and mins are either critical points or endpoints. A critical point is where the derivative of the function is 0 or undefined, and it's in the interior, assuming the point exists. Although it is possible, however, you could have an extrema at an endpoint. So we've always got to check for the critical points and check for the endpoints.
Can the critical point be an open circle?
In the original function, no. It can be undefined. The derivative can be undefined, but the original function cannot be undefined. In other words, you can't have a critical point if there is no point there. And so if you do have an open circle there, there is no point. So it can't be a critical point. Okay, so let's go back to this original graph here and let's state the critical points. So we're going to check where the derivative is equal to 0, meaning we have I'm waiting for somebody to say it's a horizontal tangent, Newhouse, because the slope is 0. Oh, okay, it's a horizontal tangent. Where is that? Okay, so f prime is equal to 0 at x is equal to c. Is there another one? There is, also at x is equal to e. Is there another one? There is not. It also has a critical point where my derivative is undefined. And there is a point where the derivative is undefined. In this case, that is at x is equal to d. And I know that it is undefined at x is equal to d because, and so how would we say that? It is not differentiable at x is equal to d. It's not differentiable at x is equal to d because, okay, the slope on the left-hand side is not equal to the slope on the right-hand side. Therefore, it is not differentiable. All right, so you need to know extreme value theorem, critical points, how to find an extrema, either from the critical points or the endpoints. And we're going to look at several examples today, starting with, let's talk first about vertical tangents and horizontal tangents. So a horizontal tangent, again, the slope is equal to 0. If I have the cubic parent function here, y is equal to x cubed. At x is equal to 0, the slope is equal to 0. So is there a critical point? Well, is this point in the interior? Yes. Is the derivative equal to 0? Yes. Is it defined? Yes. Therefore, this is a critical point. So now let's compare the horizontal tangent to the vertical tangent. Like I have a function here, x raised to the 3/5 power. Here, my slope is going to be undefined because I have a vertical tangent straight up and down. So is this a critical point? Well, does the point exist in the original function? Yes, there are no holes in asymptote or asymptotes. Is my slope undefined? Yes. Is it in the interior? Yes, so it is also a critical point. However, I could say that it is not differentiable. It is not differentiable at x is equal to 0 in this case. Not because the slopes are different on each side, but what is my slope at 0? It's undefined. And since it does not have a slope, therefore it does not have a derivative, therefore it is not differentiable. Whereas the horizontal tangent, it does have a derivative at 0, it's equal to 0. Well, we're going to look at a few examples. But before I wade into the calculus here, I wanted to make sure that we keep in mind, sometimes students kind of get lost in the calculus and they forget the other math behind it. All right, so let me make a few comments here before we do this example. Example 2 says, use analytic methods to find whether a function is increasing or decreasing. I have a function, f of x is equal to x minus 1 squared minus 2. What type of function is this? It is quadratic because the degree is 2, which means that it is a parabola. Does the parabola open up? Excuse me. It does. How do we know that the parabola opens up? There is no negative in front of the variable. So look, it's just going to do that. Right? Does it have a max or a min? It's got a minimum because it's opening up. The minimum is going to be at the vertex. Therefore, on the left side of the vertex, it is going to be decreasing. On the right side of the vertex, it is going to be increasing. And so this is a pretty easy example, right? Because I should know all this without doing any of the calculus. But let me show you how the calculus works. All right, so the first thing we need to do is we're going to take the derivative. I'm going to use my good friend, the chain rule. The 2 comes out front. The x minus 1 comes down. I multiply by the derivative of the chocolate there, which is just 1. And so then after we take the derivative, we want to find the critical points, which means we would need to find where the derivative is either undefined or 0. So looking at this, I have 2 times x minus 1. The derivative is not undefined because if I look at 2 times x minus 1, there are no holes or asymptotes in that. So it is not undefined. It is equal to 0, however. And so if I take 2x minus 2 and set it equal to 0, I get 2x is equal to 2, therefore x is equal to 1. So my derivative is going to be 0 at x is equal to 1, which is the vertex of the parabola. And so going back to the question, it says use analytic methods to find where the function is increasing or decreasing. So I need to find where the function is increasing or decreasing. I should know it, right? Because it's a parabola. But using calculus, what shows increasing or decreasing? Positive or negative what? Slope. And the slope is the derivative. So I need to find where the derivative is positive or where the derivative is negative. So I'm going to use pre-calculus, my sign charts, right? Where have you gone? Pre-cal. We're going to do a sign chart. Do we remember sign charts? Well, they're not too bad. You just need to know that we are plugging into the derivative because the derivative shows the slope and the slope shows whether it is increasing or decreasing. And I'm going to take my potential critical point that I found here, which is x is equal to 1. And I'm going to check values on either side of 1. All I care about is the sign. And again, I'm plugging it into f prime. So I'm going to pick a point on the left side of 1, let's say 0. If I take 0 and plug it into the derivative, I've got 0 minus 1, which is negative 1. Negative 1 times 2 is negative 2. Therefore, it is negative. And I knew it was negative because it's a parabola that opens up. And then if I take a point on the other side of 1, let's say 2, and I plug it in, I've got 2 minus 1 is 1. 1 times 2 is positive. Therefore, I can say that this is decreasing from from negative infinity to 1, and it is increasing from 1 to infinity. And is there a critical point at 1? Yes. And the problem did not ask this, but this is going to be a minimum because it's going, the function is going down, it's decreasing, and then it goes back up. It's increasing. Okay, so let me pause right there for just a second. Any questions on that example?
How do you get undefined for again?
Usually it's going to be undefined if you have a denominator and the denominator is going to be 0. Or maybe you're taking the square root of a negative number or something like that. But in this case, I just have 2x minus 2. And if I were to graph that, it would be a straight line, right? There's no holes or no asymptotes in that line. There's no point where it is undefined. Therefore, the derivative is not undefined in this example. Okay. Wait till we get to the next example. I think it'll make a little bit more sense. All right. So, second example. I have k of x is equal to 1 over x squared. I'm going to write this as x to the negative 2. And I need to find the derivative, analyze it for critical points, make a sign chart for where it's increasing or decreasing, and then check for my critical point. So first step, I need k prime, which is going to be negative 2x to the negative 3. It's a simple power rule. And I'm going to go ahead and write it like this, negative 2 over x cubed. So now I want to check for when the derivative is equal to 0. And that is never in this case. Why can it not be equal to 0? Well, I have a fraction here, right? And the only way the fraction could be 0 is if my numerator is 0. And my numerator can never be 0 because it's always negative 2. Therefore, I can ignore this one. It is undefined, however. And it's going to be undefined if I have a rational function when my denominator is equal to 0. So I would take the x cubed and set it equal to 0. And that's going to tell me that it is undefined at x is equal to 0. Now I'm going to go to my sign chart. And I'm plugging into k prime. You're plugging into the derivative. So I'm going to pick a point on the left side of 0. Let's say negative 1. If I plug in negative 1, I get negative 1 cubed, which is negative 1. Negative 2 divided by negative 1 is positive 2. So this is positive. Then I'm going to pick a point on the other side of 0. Let's say 1. And I'm going to plug in 1. That's going to give me negative 2 over 1, which is negative. Therefore, I can say that this is increasing from negative infinity to 0. And it is decreasing from 0 to infinity. Is there a critical point at x equals 0? The answer to that is no. Why? Why is there no critical point? If my derivative is undefined here. Well, what happens if I plug 0 into my original function? There's not a hole there, there's a what? There's an asymptote in the original function. So can you, it's a philosophical question, can you have a point if the point does not exist? No, okay, so remember I said a critical point, it's got to be in the interior. The derivative has to be 0 or undefined, and the point has to exist in the original function. So if I take 0 and I plug it into the original function, I've got 1 over 0, I'm dividing by 0, and that is undefined. Therefore, the point does not exist, therefore there is no critical point. Okay, so the answer to this is no, because it does not exist in K of X. So when a function changes from increasing to decreasing, this is a possible maximum. And in shorthand, we can say f prime changes from positive to negative. And when a function changes from decreasing to increasing, this is a possible minimum. In shorthand, we would say f prime changes from negative to positive. And I say possible because in this case, for example, it changes from positive to negative, but it is not a max. And it is not a max because it is not a critical point. And it is not a critical point because 0 does not exist in the original function. So you can't have a maximum if the point doesn't exist. Okay? But we will use sign charts to analyze and find extrema. So if I'm looking at the sign chart of the derivative and it changes from positive to negative, that would indicate a maximum, assuming that the point exists. Okay? Let me pause right there. Questions for me?
Are you always going to plug in 0 or K prime? Okay.
Yes, we want to know because a critical point is where the derivative is 0 or undefined. So we want to find the value that makes the function, the derivative of the function 0 or undefined. All right, turn the page, please. We're going to do a couple of more examples and then we will call it a day. So let's take this one step further. Example 3, use analytic methods. That means no calculator. We're going into the calculus jungle to find whether the function is increasing or decreasing and state the x values of any extrema. All right, so here, this is the process. We take the derivative. We analyze the derivative to see where it's 0 or undefined to find potential critical points. If they ask about increasing or decreasing, I'm going to do a sign chart plugging into the derivative. And then I may need to find extrema based off the sign chart and the potential critical points. All right, so here we go. First thing, you don't have to do it like this. You can do the quotient rule, but I'm going to write this as x squared minus 1 raised to the negative 1 so that I can use my good friend, the chain rule, to get the derivative. So the derivative f prime of x is going to be negative 1. X squared minus 1 comes down. I subtract 1 to give me negative 2. And then I wouldn't want to forget the derivative of the chocolate, right? And lose points on my test, for example. All right, so I need the 2x out there multiplied. So now I'm going to clean this up just a little so that I can work with it a little better. The negative exponent is going to move to the bottom. So that's going to leave a negative 1 times 2x. in the numerator, so I'll have a negative 2x in the numerator. And then an x squared minus 1 squared, that becomes positive when I move it to the denominator. So now I need to analyze the derivative and see whether the derivative is undefined or 0. So f prime equals 0 at, it's going to be x is equal to 0. I take negative 2x, excuse me, and set it equal to 0. That gives me 0. And then f prime is going to be undefined whenever x squared minus 1 squared equals 0. So solving for this, I take the square root of both sides and the squared goes away. So I have x squared is equal to 1. So x is equal to plus or minus 1. And so I'm going to make what is called a consider list. My consider list includes my critical points and my endpoints. There are no endpoints in this case because it is not bounded. Okay, so I can ignore those. And my potential critical points, I've got 1 and 0, and then plus or minus 1. So x is equal to 0, x is equal to 1, x is equal to negative 1. These right here, where the derivative is 0 and where the derivative is undefined, are my potential critical points. Now I'm going to make my sign chart. I got negative 1, I got 0, and I got positive 1. And I'm plugging into f prime. Yes.
So if there's a fraction as the derivative, find f prime equals 0.
You look at the numerator.
Okay, and define the denominator.
Correct. Because if I have 0 over 2, for example, then that value is 0. But if I have 2 over 0, then that's undefined. So yes, anytime you have a rational function for your derivative, you're going to look at the numerator for when the derivative is 0 and the denominator for when it's undefined. If it's just like a simple linear function, like one that we did before, it's not going to be undefined, but it could be equal to 0. All right, so here I'm going to pick values on either side of these points to do my sign chart. But I want you to notice in my derivative, the denominator is squared, meaning that it is always positive. So I really just can ignore the denominator because it's always positive at this point, and I'm just looking at the numerator. So if I pick a point on the left side of negative 1, let's say negative 2, and I plug it in, I get negative 2 times negative 2, which is positive 4. Therefore, it is positive. If I pick a point between negative 1 and 0, let's say negative 1/2, and I plug it into the numerator, I've got negative 2 times negative 1/2. That is also positive. All we care about is the sign, nothing else. So if I pick a point between 0 and 1, 1/2, that is going to be negative. Negative 2 times 1/2 is negative. And if I pick a point on the other side of 1, let's say 38 million, and plug it in for x, that's going to be negative. So I got plus, plus, minus, minus. Okay, so I can say that it is increasing from negative infinity to 0. And it is decreasing, based on my sign chart, from 0 to infinity. And now I'm going to check for possible extrema. Is it a max or a min at negative 1? Based on my sign chart. At negative 1? It is not, but it's neither a max nor a min because in my original function, check the original function, right? What is there at positive 1 and negative 1? Both of those values make my original function undefined. Therefore, I have an asymptote in my original function. Therefore, I cannot have an extrema. Okay? There is an extrema, however, at 0, and I know that it is a maximum because it goes up, then it goes down. Okay, it changes, the derivative changes from positive to negative, and 0 exists in the original function if I take 0 and plug it in. So I know there is a max only, I don't want to say that, sorry. I want to say there's a max at x is equal to 0. There's only one critical point because I'm going to say x equals plus or minus 1 are not in the domain. Because there's an asymptote in the original function. All right, I think I'm going to do one more and then stop there for the day. All right, so in this one, they give me the derivative. Thank you very much. I can skip the first step, right? So they give me the derivative g prime of x. So again, once you have the derivative, we're going to analyze it for when the derivative is equal to 0 or undefined. Do a sign chart to check the increasing or decreasing, and use that to find the critical points and the potential extrema. All right, so I need to find when g prime is equal to 0. So again, I'm looking at the numerator. I'm going to take 4x plus 8 and set it equal to 0. That gives me x is equal to negative 2. And then I want to find where g prime is undefined. And that is going to be wherever my denominator is equal to 0, which in this case is at x is equal to 0. And the way that you find that is you would take 3x to the 2/3. I'm going to go ahead and write this as 4x plus 8 over 3 times the cube root of x squared. And I set that equal to 0, and I get x is equal to 0. So this tells me that I have 2 possible critical points. 2 possible critical points. One at x is equal to negative 2 and one at x is equal to 0. So let me do my sign chart. This is g prime. I've got negative 2 and I've got 0. Look at the variable in the denominator. The variable is squared. It's x squared. Therefore, it is always positive. So I'm going to ignore that and only look at the numerator, the 4x plus 8. If I pick a value on the other side of negative 2, let's say negative 3, on the left side of negative 2, rather, I plug in negative 3, I get negative 12 plus 8, which is negative. And then I want to pick a value between negative 2 and 0. Let's say negative 1. 4 times negative 1 is negative 4 plus 8. That is positive. And then pick a value on the other side of 0. Let's say 1. I plug that in. That is also going to be positive. So we are going to be increasing from negative 2 to infinity. We are decreasing from negative infinity to negative 2. Is there an extrema at 0? The answer to that is no, because it is increasing and then increasing. Okay, there's no sign change. However, I could say there is a minimum at x equals negative 2. Because f prime changes from negative to positive. And I'm assuming there, I probably should have said something about it, but I'm assuming there that -2 does exist in the original function. We don't have the original function to look at it in this case. Okay? Questions that I can answer on that example?
Okay, so when you plug